Okay, so we're going to talk about infrared spectroscopy. I do have a handful of slides kind of on some background information. That is not going to be our focus today. Our focus is going to be the purpose of the instrument and how to read the data that we get from the instrument. We're going to talk a little bit about the background though, so that it will hopefully kind of make sense when we start to talk about the data. Eventually, we're going to talk about 4 different pieces of instrumentation. This is the only one we talk about in this semester. So right here is where we are. Each of these pieces of instrumentation is going to give us different information. So an IR, or an infrared spectroscopy, is going to tell us functional groups. Now, what I mean by that is when we're in the lab, and we're going to do this in beyond labs as well. So whether we're in a real lab or a digital lab, there is an instrument called an IR, or an infrared spectrometer, and we can put some of our sample, some of our product into that instrument, and we get a graph. And the information that we can learn from the graph, or its official name is a spectra, but you know, it's a graph. The information that we get from an IR graph is that we can learn what type of functional groups our product has. So I have a table of some functional groups here. Eventually, we'll also talk about mass spectrometry, and that is going to tell us about the molar mass and the molecular formula of our compound. Sometimes we can get some structural features from it. There's actually a lot of information you can get from a mass spectra or a graph. We'll go into some of it in next semester. We don't go into a whole lot of details on it though. The most powerful tool in organic chemistry is nuclear magnetic resonance spectroscopy, or much simpler to say, NMR. NMR is going to tell us about the carbon-carbon structure and the carbon-hydrogen bonds within a molecule. That's a lot. That's giving us almost all the information of an organic molecule. And then the last one, which is probably the least important, is ultraviolet visible spectroscopy, or UV-Vis, and it tells us about conjugated double bonds. So it has a very, very specific purpose. So with all of these pieces of information together, we can have an unknown. We could have just a pile of powder or a liquid in a vial, and with all of this data, we could figure out what our unknown is. And so that's actually the first thing we'll do next semester. Your first test in the fall will be, so I always call it a take-home test. So for in person, it will literally be a take-home test. If we are digital, if we're Zooming still, hopefully not, but if we're Zooming still, it won't be a time test. You'll just have, you know, a week to do it. But what it will be is a bunch of these graphs, and you have to figure out what your unknown is. So for in person, we'll have class time to work on it and talk about it. So I hope that's what we get to do. It ends up kind of as fun as a test can be. It ends up being kind of a fun test because it means that there's a lot of discussion involved. All right, weird little side note, but what we're focusing on in this chapter is IR. So we're going to use our data to figure out functional groups. Background info. Infrared is on our ultraviolet, gamma ray, visible light spectra, our electromagnetic spectrum. Nope, wrong one. One more over. There's our infrared right there. So it is lower in energy than our visible light, but it's in the same family. It's a type of light. This is all Gen Chem stuff, relationship between frequency and wavelength. We'll kind of get into that. But the big thing is that wavelength and frequency have an inverse relationship. So a bigger wavelength means a lower frequency. A bigger frequency means a lower wavelength, you know, opposites. What happens in an IR machine is that we are going to And I don't even think this slide is, I'm just going to skip this slide. And I will stay there. Okay, sorry. I was trying to shorten this down. I was decide what slide I need to be on for shortening. All right. What happens in the infrared machine is we're going to take some infrared light. We're going to shoot it at our sample, and there's energy in it. And so when that energy hits our sample, it's going to cause it to vibrate. These are the different ways that it can vibrate. And there's actually a lot more than this. These are just the main ones. And we focus on the stretches. So there's a symmetrical stretch and an asymmetrical stretch. There's also a lot of different types of bending, which is the bottom four. But really, the idea here is that as the energy, that infrared light hits the molecule, hits each individual bond, it can cause the bonds to get excited, which really, remember, just means they've gained some extra energy, and they release that energy through movement, so through kinetic energy. Infrared is a range of wavelengths, and so we're going to use every wavelength possible because not every bond will be able to absorb every wavelength. There are energy specifications. So one of the things we learned about energy back in Gen Chem is that it is quantized. So that's why there was a ladder a couple slides ago. Remember, quantized means that the electrons can be at this energy level and they can be at this energy level, but they can't be in between. So we often use a ladder to describe that. Some bonds have big energy gaps. Some bonds have little energy gaps. So the one with a bigger energy gap is going to absorb infrared at a lower wavelength because low wavelengths have a higher energy. And a bond that has a smaller energy will absorb the infrared light that has a smaller energy or a bigger wavelength. And so it absorbs that energy, it does some moving, and then it releases that energy. And we get a graph. So this is the graph that we get, or again, it's a spectrum. The way that we read this graph, or what it's telling us, is that we have percent transmittance on the y-axis, and we have wave number on the x-axis. So percent transmittance is telling us how much of that infrared light passed through the sample. So if it's all the way up here close to 100%, that means that all of the infrared light that was at this energy level passed through the sample. None of it got absorbed, so none of the bonds had that energy level. But when we have, and this is, I know it's kind of upside down, so when we say the word peak, this is a peak. This is a peak. These are smaller peaks, but they're peaks. So when we have these guys down here and the transmittance is close to maybe 5% or 15%, we're saying that almost all of that energy got absorbed by the molecule and only 5% of it was transmitted through the molecule. So whatever this energy is right here matches the energy of one of the bonds in our molecule, or maybe a couple of the bonds in our molecule. So I'm gonna erase all my scribbles. So when we're looking at our graph, what we want to look for are these peaks. That's going to give us information. That's going to give us information. And the ones that are closer to the bottom, so the ones that are longer, are going to give us, that's not, I was going to say something, it wasn't going to be completely true. The ones that are longer towards the bottom are definitely going to be the ones that are easier to pick out, but ones like this are also going to provide us with information. We do have labels for these to say like how tall they are. So these ones would be strong peaks, and these would be medium peaks. The ones that are a little bit tricky are the ones that are considered to be weak peaks. Like these two little guys right there, they might be important, but it can be hard to tell sometimes the difference between a peak that is important, that just happens to be weak, versus noise or just a carbon-hydrogen bond, because we know there's going to be a lot of just carbon-hydrogen bonds in there. So we can label them as strong, medium, or weak. How to figure out if it's important or not, honestly, just kind of takes some time. Sometimes it takes a little bit of guessing. Reading these graphs is mostly science with a little bit of art thrown in, so a little mix there. Let's talk about the x-axis though. So the x-axis is wave number. There's a little equation up here at the top, up here. This is wave number. So it's a nu, like NU with a tilde on top of it. It's equal to the frequency divided by the speed of light. The computer does all that for us. We don't need to know the actual equation. That is what it is. And so that just means that we have over here where it's 4,000, this is high frequency, but that also means that it's high energy. And then on the other side, we have low energy. So we have high energy and we have low energy. One thing I want to point out about the x-axis, which is a little bit weird, but it's also pretty common with these types of graphs that we're going to look at through all of the instrumentation. Notice the spacing. So between 1,000 and 400, so that's a difference of 600 right there. But then notice from 4,000 to 3,500, that's a difference of 500. I point this out because the spacing is not consistent. The bottom half of the graph is much more spread out. And then let's say the right-hand side of the graph is much more spread out. And then the left side of the graph is a little bit more compacted in together. And this is standard. This is how the computer processes the data and presents the data. The reasoning for it, though, is because in the right-hand side of the graph, there's going to be a lot more peaks that are closer together. So we actually do want them spread apart a little bit more. And on the left side of the graph, there's going to be less peaks. And so if we squish them together a little bit, it's okay. So there's kind of it's really just a visual reason why we do that, but it is something that the computer is doing for us. I pointed out because if we have to estimate, like if we want to know, okay, where's this peak at? And we want to do a little bit of estimating to figure out where it's at on that scale, just realize that the scale on each half is different from one another. Questions on just kind of the start here of our graph? Okay. When we're looking at the graph, there are going to be 3 things that we're going to pay attention to. The first one is the wave number. So the wave number is where it's at on that x-axis. So we're going to look at wave number. We're going to look at intensity, so whether it's strong, medium, or weak. And then we're going to look at the shape of the peak. So we're starting with wave number, though. Wave number is going to depend on a couple things. It's based on Hooke's law, but the 2 big things that it's based on is the strength of the bond and the mass of the atoms involved. So let's look at bond strength first. So these 3 over here. We have a carbon-nitrogen triple bond versus double bond versus single bond. And so the triple bond is going to show up at about 2,200. Notice the units there, it's centimeters to the -1, or the other way we could write that is 1 over centimeters. You can also say it as inverse centimeters, but 2,200 about. The carbon double bond, 1,600. The carbon single bond, 1,100. A triple bond is stronger than a double bond is stronger than a single bond. So as we increase in bond strength, we're going to have a larger wave number, or it will be farther to the left on our graph. Oh, that's actually something else. Let me point that out on our graph. You probably realized this because I was pointing it out, but I didn't actually like explain it or say it. Notice that on the left side is the big number, 4,000. And on the right side is the small number, 400. This is the opposite from what we normally see if we were to actually just graph data, like in a math class. It is supposed to be that way. I honestly don't know why we do that, opposite from what we would expect to see in a math class, but it's always that way. So this would be on the left side of the graph, and this would be on the right side. The four bonds that are shown over here, carbon bonded to hydrogen, deuterium, oxygen, and chlorine. Deuterium is a hydrogen with a neutron. So it's a hydrogen with a mass of 2. We will see this pop up in the book occasionally. It's really just a way to label a hydrogen or have what's called a heavy hydrogen. But what's shown here is 4 atoms increasing in mass. So hydrogen's the lowest mass, chlorine is the highest mass. And we go from 3,000 to 2,200 to 1,100 to 700. So a smaller mass is going to give us a larger wave number. So the carbon-hydrogen bonds are all going to be around 3,000. So that's all the way over here. Notice there's nothing else over there because hydrogen is so light that it puts it up in its own little category. And then we have our triple bonds here in the middle, and then our double bonds, and then carbon single bonded to our other atoms is on the far right side of our graph. And we have them broken down 1,100, 700 into categories based off of how much it weighs. So that little chart on the bottom is definitely a very, very basic division. I have a couple other charts later on that show a little bit, well, show a lot more information really, but that's kind of a good way to think about it. This isn't something you have to memorize where you would find these, but for quick reference, something like this could help you kind of map it out in your brain a little bit. When we're looking at wave numbers, reading this graph can be a little bit complicated. And so we actually divide it into 2 categories. And when we read the graph, we want to start by actually drawing a line at 1,500. Do I have? No, okay. I wasn't sure if I had lines added in animation or not. So we divide the graph at 1,500, and the left side of the graph is the functional group region. So that's where there are less peaks that are a little bit farther apart. The right-hand side of the graph is called the fingerprint region. And our divider line is about 1,500. So we categorize the left side as about 4,000 to 1,500. And then the right side is 1,500 down to about 400. So what we're looking at in these 2 structures, we have a pentane chain. And the top graph has the alcohol and carbon number 2. The bottom graph has the alcohol and carbon number 3. It's the only difference between them. The functional group regions of both graphs are identical. We have this big wide peak and then this kind of jagged peak, big wide peak and jagged peak. The reason why they're identical is because they have the same functional group. They both have that alcohol and they both have a bunch of carbon-hydrogen bonds. So that portion of the graph is going to tell us the same information. The fingerprint region of the graph is literally a fingerprint of that molecule. So we can see that there's differences. The one on the bottom has this big wide peak. The other one doesn't have that. This one on the top has kind of that double peak, and the one on the bottom doesn't have that. The peaks that are in that lower region, that 1,500 to 400 region, are giving us detailed information about the actual structure of the molecule. So it is telling us where that alcohol is at. It is much, much more difficult to read that side of the graph because there's usually so many peaks that are overlapping that it can be very difficult. If we're trying to tell 2 molecules apart, so if we're comparing them, then we can use it for comparison purposes, but just to look at those peaks and analyze it, there's honestly so many peaks that it can be a little bit difficult because it can be interpreted in so many ways. So we're definitely going to spend most of our time at that 1,500 and above in that functional group area. Next one on wave number. So we're still in that wave number section. And notice what area we're at in the graph. So we're up in that 3000. And all of these have a line, a red line at 3000. And the reason that that line is there is because that's going to help us see the difference between alkanes, alkenes, and alkynes. When we have peaks below 3000, that is an sp3 carbon. So we're almost always going to have some peaks right there. So at that 2900 mark-ish, because we're almost always going to have some carbon-hydrogen bonds. When we have a peak just on the other side of that 3000 line, so this is at like 3050-ish, that's an sp2 hybridized carbon bonded to, no, did I say that right? sp2 hybridized carbon bonded to a hydrogen. And then when we have an alkyne, notice that it is closer to 3300-ish. So as that hybridization increases, we get stronger bonds. And we already said on a couple slides ago that stronger bonds make the peaks shift over to higher numbers. So this isn't any exception to that. So having that line at 3000 helps us see those differences. All right, one more in wave number. The last one in wave number is looking at resonance. So I'm gonna skip a bunch of slides here for a second. There's tables like this. So I Googled IR table just to find one online so I could steal it and put it in my slides. But what we will see is ketones. A ketone peak is right around 1715. And I say right around, so look at the ones above it. There's some ranges there. What's around that ketone or ester or aldehyde, whatever it might be, is going to affect where it actually shows up. So the numbers on these tables that you'll find are going to be approximate because those numbers can be shifted by the environment. So let me go back to our slide we were on. So we have our ketone at 1720, and even that's a little bit different than what the table said. But when we have a double bond that's next to it, this is called a conjugated ketone, it puts it at a lower number. It puts it at 1680. And so the table might not tell you that. It might not say a conjugated ketone is going to be at 1680. This is something that we need to see on our own or realize or recognize on our own. The reason for it, when we have this resonance contributor, the resonance hybrid is going to look something like that. And so we have all the partial charges in it as well. But what that means is that this is not a pure double bond. It's like a bond and a half. So a bond and a half is going to be weaker than a double bond. And so conjugation is going to lower that wave number. More delocalization means a lower wave number, so a lower number on our chart. So when it's next to an alkene or next to a benzene ring, it's going to bump that number a little bit lower. Okay, so we've had like 4 or 5 slides on wave number. We've talked about why it will show up in certain areas or why it will be higher or lower. Most of the wave number information we get is going to be from a table, like I showed you though. So there are tables like that in your book in chapter 14. I was looking to see, I can't remember if our book has it. No, that's pKa. Sometimes like the cover of the book will also have a table, and that's the periodic table. Okay, so in chapter 14, it does have a table for you. If you have the lab textbook, the IR technique section also has a really good table, as well as like a kind of like a question list of how to look at the graph. Like it directs you to look at certain areas and ask questions. Does it have a peak here? Okay, if it doesn't, does it have a peak here? And so it kind of directs you to go through that. And so all of that is looking at where the peaks are located in your graph. And we're definitely going to practice this. We're going to look at some together, and then that's what the worksheet is today as well. But we've done the wave number section. So we have 2 more categories to talk about. The next one is intensity. And so this is the difference between a strong peak and a medium peak. These ones up here, I know they're not labeled on here anywhere, but we would label these as a weak peak if we wanted to discuss them. The difference between strong, medium, and weak peaks is dipole. When we have a bigger polarity, we're going to have a stronger signal. So notice the 2 that are over here. We have a carbon-oxygen double bond versus a carbon-carbon double bond. Carbon-oxygen double bond is definitely going to be a more polar bond than a carbon-carbon double bond. And then the last bullet point, if we have a symmetrical molecule, that can cause the molecule to not be polar, to cause it to be nonpolar. And where we would expect to see a peak, we might not actually get one because of that symmetry. So the idea is as that bond stretches, because it's not going to have a difference in polarity, the stretching is going to be so symmetrical that it's going to cancel out. So having a symmetrical alkene or a symmetrical alkyne, they don't always show up on our IR graphs, and so they can be a little bit harder to identify. All right, so there's our difference. Stronger peaks are going to involve heteroatoms. Medium peaks or weak peaks are going to be just our carbons and hydrogens. And then the last group is the shape. And the shape is going to be very helpful in specific areas. So just like we could label strong, medium, and weak, we can also label our peaks as broad. This is a narrow peak in that second picture, but the official label that we give it is sharp. So broad versus sharp. If we have hydrogen bonding, it makes the peaks wider. So hydrogen bonding will give us a broad peak. So we would expect to see this with alcohols. There's a couple other things, though, that we see it with. One of them is carboxylic acids. So here's our carboxylic acid peak. It's very broad. And it also gets these extra little peaks because it's actually overlapping with the carbon hydrogens. So I'm gonna go back a couple slides, point something out. Let me do a little erasing just to make it neater. Oh, it won't let me. Oh, there we go. So this broad peak right here, that's the OH bond. And then these peaks over here, that's the carbon hydrogen bond. And so we have that nice broad, wide peak for the alcohol. When we see a carboxylic acid, though, it becomes so broad that it overlaps with those carbon hydrogen peaks. So one of the ways to think about it or remember it is that it looks like a hairy beard. So it's not smooth. It's kind of a little bit jagged. And is it on the next slide? Oh, I think it's in 2 slides. I have a little picture that I saw online a few years ago that I keep using, but it's kind of a reminder for all these different shapes. Another shape is whether we get 2 peaks versus 1 peak. So we have a primary amine versus a secondary amine. And because that primary amine has 2 hydrogens attached to it, we get 2 peaks. And because our secondary nitrogen only has 1 hydrogen, we only see the 1 peak. And so these are in a pretty distinctive area. They're pretty high up there. They're both around about 3,300. There's not a whole lot of other stuff that shows up in that region, but seeing either 1 peak or 2 peak tells us what type of nitrogen we have. All right, here's the picture that I like. So between about 3,200 to 3,400, we will see alcohols amines, and carboxylic acids. And the shape of that peak will tell you which one it is. So our alcohols are smooth tongues, so they're that rounded shape. And our carboxylic acids on the bottom there are the hairy beards. And then the amines, if it's a primary amine, we get vampire fangs. And if it's a secondary amine, we get just one sad little fang. The other thing that shows up right here is the terminal alkyne, so that hydrogen on the end. But it's a little silly picture that hopefully sticks in your head so that as you're looking at those shapes, you can see things in the shapes a little bit better. So one more of those. Okay, now questions at all about the shapes or the intensities? Okay, so let's talk about how to actually analyze a graph then. There's a lot of different ways to approach this. And I'm gonna tell you what page the lab textbook talks about it, because I like the way that they do it as well. But we definitely want to focus in that functional group region, so 1500 and above. So it is technique 25 at the end of the lab book, and it starts, so if you're going to use the lab book for this, it's technique 25, section 13, and it starts on page 896. So really good resource. It goes through questions. The first question says, is a carbonyl group present? And then it tells you how to look for that. I'm going to stay over here. All right, so here's how we're going to look at this. It tells us we're going to focus on the diagnostic region. So really we're going to start at 1500 and above. And in the 1600 to 1850, we're looking for double bonds. 21 to 2300, we're looking for triple bonds. 2700 to 4000, we're looking for things bonded to hydrogens. And this is the two areas there. So notice there's a line at 3000. Below 3000 are just regular carbon hydrogen bonds. We're definitely going to see those in our structure. And then above 3000 is where we will see alkenes, alkynes, amines, OHs, so whether they're carboxylic acids or alcohols. That's this. Kind of skipped ahead, but there it is. It's written out here in a pretty simple way. It takes a lot more effort than what I've literally read, but we're going to go through it and look at how to analyze this. So I have a couple example ones. Oh, I have a couple graphs first. I liked this one because it was nice and visual. So we have 3600 all the way over here, 500. So notice at 1500 and less, it's in green because it is that fingerprint region. But it has all the areas. So we have carbon oxygen double bonds. We have all of our things bonded to hydrogens over here. We have our triple bonds in the middle. So notice we have single bonds, double bonds, or excuse me, single bonds, triple bonds, double bonds. And then we have some more information in that fingerprint region that we will use very sparingly. But it's kind of a nice way to look at it. It's telling us whether we expect the peaks to be strong, medium, or weak, broad or narrow. Variable just kind of means that it could be any of those categories. It depends on what's surrounding it. So nice little visual. This is the other one that I already showed you. Again, I just got this one off the internet and I searched IR analysis table and found one. So of course, there's a lot of good resources out there. I liked this one because it was color coded. So we have all of the carbon oxygen double bonds in the middle there that are highlighted in yellow and orange. And then all of our things bonded to hydrogens at the top. when you are looking at tables like this and using them for your analysis, before you start to use the table, look to see how it's organized. So this one is organized by wave number. So we have 3640 all the way down to 1450. So notice that this doesn't even go into the fingerprint region, which is completely okay, but it's in order of wave number. I prefer tables that are listed in order by wave number. The other way to do it is that you might see tables listed alphabetically by functional group. That can make it a little bit harder to analyze, especially in the beginning when it's new. So just something to look out for. All right, let's do some analysis. So here's our IR spectrum. Here are some potential structures that could have made this graph. And so our job is to figure out which of these structures made this graph. And so I'm going to start by drawing a line at 1500. There's my line. I know that in the 1600 to 1850 region, so 16 to 1850, this is where we would see carbon-oxygen double bonds, carbon-carbon double bonds, and there's nothing. There's nothing right here at all. There's no peaks. And so that means that I can say that it's not A, it's not B, it's not C, and it's not F. All of those had double bonds. And so because there isn't a peak in that area, we can cancel all of those out because it doesn't match with our graph. Questions about that so far? I just crossed out a whole bunch of options. Okay, so the next area, we're just kind of moving down the line. If we go from 2100 to 2300, this is triple bond region. So carbon triple bond, carbon nitrogen triple bond. We don't have any peaks right there either, but we also don't have any options that had triple bonds. So, and then the last area is going from 2700, so right here, all the way to 4000. So really the rest of the graph, this is stuff bonded to hydrogen. And I say stuff bonded to hydrogen because it's everything else. And to analyze this area, we actually want to draw this line right at 3000 here. And so we know that going from 3000 to 2700, these are just carbon hydrogen bonds with alkanes. So we have those. And if we look at what's left, they both have carbons bonded to hydrogens from single bonded carbons. And really all of our options had that. And most structures that you're going to use will have that. Above that line, we don't have any peaks right above it, right here. That would be a carbon hydrogen bond that was an alkene. But we also already eliminated all of our alkenes, so we know that we're good there. But we do have this nice broad peak right here. And so where that nice broad peak is at is that we have a peak right at, let's see, where are we at right here? Right at about 3300. And because of its shape, that tells me that it's bonded to an oxygen. So this goes back to the shapes of alcohols versus carboxylic acids versus our amines. And so because of that, we know it's not letter D because we don't have a hydrogen bonded to that oxygen. So that leaves us with one option. That leaves us with letter E right here. It has carbon hydrogen bonds, which are going to be the peaks at about 2900. And we have the peak at 3300, which is from the OH bond. None of the other structures fit with that data. Questions about that analysis at all?
Wait, can you explain the last part again with the 3300 and the CH?
So really the only peaks on this entire graph are the one right here that's at about 2,900. And a peak at 2,900 tells us that it's an sp3 bonded carbon bonded to a hydrogen. And really all of our structures have that, so that doesn't really help narrow it down. But the peak that really solidifies it for us is this big broad peak right here that's at about 3,300. That, and it's a broad peak, that is an oxygen-hydrogen bond. And so we know that because of its location, it's at about 3,300, and because it has that nice, smooth, broad shape, that tells us that it's an alcohol peak. And so our only structure that fits with that is letter E, because it has that alcohol in it.
So if it was broad, it's always going to be OH?
Yeah.
Okay. Thank you.
Yeah, OHs are really nice because they make it's easy to pick them out. And the question in the chat asks if this will be on the test. So yes, there will be some IR questions on the test. And it will probably be something like this, where you'll be given an IR and you'll be given some options of which structure made the graph. And so you just have to pick out which one it is. I couldn't ever just give you a graph and not give you the options and say what made this, because remember, all the IR tells us is functional groups. So if we looked at this, we could say, yeah, that structure has an alcohol in it, but we wouldn't know if it had 5 carbons, 10 carbons, if the carbons were in a ring. There wouldn't be enough information. We could just say what functional groups the structure had. Any other questions about this first one? Okay, I think do I have one more or 2 more of these? One more, okay. Sorry, I have something in my eye. All right, one more. So we actually have the same options here, same structure options. So I'm gonna start again by drawing my line at 1,500. So I'm doing that, and really what I'm doing is I'm ignoring everything over there. I'm ignoring that fingerprint region, and majority of the time, we will be ignoring the fingerprint region. Next semester, we'll start using it a little bit, but this semester we don't need to. Okay, so then I'm gonna just kind of move from right to left. The first spot we're gonna look at is actually, let me color code this as we go through. We're gonna start 1,600 to 1850-ish, and this is our double bond region. And we got a nice strong peak right there. And our nice strong peak is at, let's see, it's at right there. So that's at about 1640-ish. Now, we know that it has a double bond. So based off of the fact that it has a double bond, we know that it can't be letter D or letter E. A, B, C, and F all have some type of double bond. So we've narrowed down a couple of them. The next area we look at is from about 2,100 to 2,300, and that's our triple bond area. And again, there's no peaks there. Yeah, there's kind of a little blip right there, but that's not big enough to be a peak. We don't care about that guy. He's too small. And also, none of our structures have any triple bonds in them. So not really an area we need to focus on. So then we move down to our 2,800 to 3,500-ish area. And this is stuff bonded to hydrogen. And we like to start this area. See if I can draw a straight line. Drawing a line at 3,000, because we know that all of these peaks over here, this is an sp3 carbon bonded to a hydrogen, and our structures have that. Everybody has sp3 carbons. Letter B only has one sp3 carbon, but it has one. All the rest of them have quite a few. So that doesn't help narrow it down, but we can assign what those peaks are. We know what caused them. The peak that could be of interest, though, that could be useful is this one over here. So this one's it's right at about 3,100, it looks like. And a peak that's at 3,100 is an sp2 carbon bonded to a hydrogen. So I'm going to go back a couple slides and show you how we know that, or where to get that information. But we're going to do a little bit of narrowing it down first. So an sp2 carbon bonded to a hydrogen, that tells me that it can't be letter A. Letter A does have an sp2 carbon. That's what's part of our double bond right there, but it doesn't have any hydrogens bonded to it. And so that narrows that down. And so that leaves us with a benzene bonded to a ketone, a alkene on one end and a bromine on the other end, or an aldehyde. So we have to get some information that will allow us to separate these three functional groups, these three structures. So I'm going to go back to one of our tables. We'll go right here. And one thing I want to point out on the table, we had that peak at 3,100, and I told you that it was a sp2 carbon bonded to a hydrogen. So you can see right here, right at 3,100, that's where our carbon double bonded, our carbon-carbon double bond to a hydrogen is at, so our alkenes. It's also where we would find aromatics. So that's really just another way to say benzene. So it's the carbon-hydrogen portion of the benzene. And notice that pretty much everything else is either too high or too low for that. So it narrows it down pretty nice and easy for that carbon-hydrogen bond. The other peak that we had was it 1640? So this one right here was at 1640. So we know it's a double bond, but we can look in our double bonded area. So that's really kind of all of this are all double bonds. And notice that all of the carbon oxygen double bonds are higher than 1640. They're all closer to 1700. But right here, 1680 to 1640, that's a carbon-carbon double bond. So that tells us that we probably have an alkene. So looking at our options, that means I can eliminate letter F. It doesn't have an alkene. But letter C and letter B both have carbon-carbon double bonds. The difference, though, this one has a ketone. So if we also had a ketone in our structure, we would have a second peak in that double bond area for that carbon-oxygen double bond, and we don't have that. So I know that I can also eliminate this one. So that leaves us with letter C here. Now, a little bit more information. If we want to, double check to make sure, I just crossed off a ketone and an aldehyde, a ketone with a benzene and an aldehyde. If I go back over here, let's see. We also have a very specific peak right here for aldehydes. And then here's where we would find an aldehyde. Here's where we would find a ketone. And then the last one is one of those, the one that had the ketone, also had that benzene ring. And when we have benzene rings, there's a couple other peaks that we tend to see. So right here for our benzene ring, or right here for our benzene ring. And so when we're trying to assign a structure, there's kind of two ways to approach it. And the way that I focused on is I looked at my peaks and I tried to assign them. The other way to do it is to look at our structures and say, well, if I did have this structure, I would expect to see a peak here. Because there were 6 structures to choose from, that means that we're trying to almost create 6 graphs in our head and then see which one matches. I feel like that's going to be a little bit more difficult. If we go with the graph we have and then figure out which one it matches with, we're only looking at one set of data. And then maybe when you narrow it down to 2 or 3 structures, then you can say, okay, well, if it was a benzene ring, we would see a peak at 1450 and we'd see a peak at 1550, and those aren't on our graph. There's nothing over here. So you can then kind of use the lack of peaks to help confirm what structure you have. This really just kind of becomes a puzzle. We want to match where the peaks are at to what could have made that, what makes that information appear there, and what structure matches that information. One of the things that can be difficult with this, let me do a little erasing here. Notice that most of these have ranges. So it's not one set number. It shows up between 1715 and 1730. Well, that's going to overlap with a lot of the other peaks. I point this out because there's overlap, it can make assigning structures that are very similar, it can make it a little bit difficult sometimes. So make sure that you are looking at the entire structure or the entire graph and not just focusing on one peak or one functional group, because it might not be enough information to distinguish between two structures if they're similar. Questions about this, about how I figured out it was letter C, about where that information came from?
Is that chart going to be available for us to like look at on the exam or anything?
Yes. So I will give you one. I probably won't be that one just because it's color coded and I'm going to assume you guys aren't going to print in color. It will probably be the one that's in the book. So let me see. I'll tell you what page it's on. There is one on page 619 of the book. And yes, I will give that to you. This is one of those things that should be readily available. So if we were in the lab class, I would tell you to print it out and put it in your lab notebook so that you can have it available. There's going to be things that you'll start to memorize, like, you know, this is where the double bonds are, this is where the triple bonds are, but distinguishing between a ketone versus an aldehyde versus an ester, that I don't expect you to memorize. So having a chart of data is going to be helpful. Because I'm going to put this one on the test, it would probably be a good idea to focus on that one and use that one. And yeah, I might, actually, no, I'll just make the decision now. That is the one I'm going to put on the test. It might not be my favorite one, but that's okay. It's one that's accessible to everybody.
Are you talking about this example specifically?
No. So this page 619 in the textbook, okay. That is the table. So I will put that table on the test.
Got it.
Yeah. Any other questions on this one? Okay, I think I have 2 more slides, ish, maybe even just one. This is showing us how we can use an IR to either compare compounds or to monitor a reaction. So one of the things we've done in Beyond Labs is we've monitored a reaction through a TLC plate. So we've watched the spots of the starting material disappear, and we've watched the spots of the product appear. We can also do that with IR. So if we look at this reaction here, we're starting with an alcohol. We know that on our graph, that would give us that big broad peak around 3,300-ish. And we're making a ketone. We know that that would give us a sharp, strong peak at about 1,700. So if we were to monitor this as the reaction was happening, in the very beginning, we would only have this peak. So this peak at 3,300, we would see a nice, big, strong peak. And then if we did another IR, maybe 10 minutes into the reaction, this peak would start to get a little bit smaller, and that peak at 1700 would start to show up. And then at the end of the reaction, this peak wouldn't be there at all, but we would have a nice strong peak at 1700. So we could actually, over time, watch the starting material peak go away and the product peak start to form. It's also at the end of the reaction, if we see that nice strong peak at 1700 for our ketone and we see a little peak over there, that would tell us that our product wasn't pure, because we can see that there's still a little bit of our alcohol starting material present. We can see that in the IR. So the IR can help tell us whether or not we have a pure product by looking for our starting material in there. And hopefully in the fall, we'll be able to use our IR spectra in lab. So you'll actually be able to make your own product and make graphs for your product. And that's one of the things you'll look for, is you'll look to see if you made a pure product, and you can determine that based off of whether you see your starting material show up in your IR or not. Okay, questions at all about this? I think this was my last slide. It is my last slide. Okay, so I'm going to stop recording. Let me do that before I forget.